All right, so let's continue our discussion related to the layout. The lecture before the last, we had obtained a layout for a. We have not discussed the characteristics, but layout of what we call it as a CMOS inverter. There's an NMOS here and then there's a PMOS here, and the gates of the two are shorted together. We apply an input here, and the drains are shorted together, and we take the output here. So that's the CMOS inverter, and we had carried out a layout of this particular inverter, and so some of the dimensions are obtained from the sizes of the transistors here. So this was taken as 3 lambda by 2 lambda, and this one was taken as 6 lambda by 2 lambda, lambda being for us 0.3. And the rest of the dimensions, they came from the various rules that were there. So let's look at this layout in a little bit more detail. So before that, once you carry out a layout, we've said that in general, design is a multi-step process, and you go from one level to the next level here. And whenever you go from one level to the next, what we call this as a synthesis step, and you have to make sure that you have synthesized the circuit properly, and therefore you have to carry out verification. And one of the ways of carrying out verification is you check, each level of design has certain rules, and you check whether those rules are obeyed or not. And the other one is to check whether you have faithfully translated the circuit from this level to the next level here. You have not made errors in the translation. All right. So, for example, in our case, we took a schematic of a CMOS inverter, and we translated it into a layout. Right. So we took a transistor schematic, we did a synthesis step. We can call it layout synthesis, and we obtained a mask layout. Right. And now, in the process of carrying this out, I can make mistakes. And mistakes can be of two kinds. One mistake is that there are, as we said, there are rules for each one of these layers that you see here, metal 1 and diffusion layer and active layers and P-well and N-wells and all that. There are rules for it, and I may have violated some of the rules. So that's one set of error that I can make. The other one is that while translating from a schematic to a layout, I may have forgotten, for example, to connect, I know there is a ground here. I may have forgotten to put a contact there. So my source is really hanging, floating. I may have forgotten to do that. Or I may not have I may have forgotten to put a substrate contact. So I can make all kinds of errors that are there, which means it's not a faithful translation of this circuit schematic into this particular one. So there are two kinds, as I said, two kinds of verification that you have to do. First one is what we call as design rule check. That all the rules that are there for, that rules that the foundry has specified for a particular technology, those rules are obeyed. And so these design rule check is something that is, as you can imagine, is very tedious, that you go ahead and look at whether all the dimensions and all that they meet the minimum requirements. So there are CAD tools which are called design rule checkers, and they'll check for all the rules, and wherever any rule is violated, they would highlight that particular part of the layout and indicate to you that this region is in violation, and they will even indicate to you which rule is being violated. So you can go ahead and correct. And normally this design rule check is being done as you do the layout. Anytime you draw a layer and something else, the design rule checker is running in the background and will check whether the rules are being obeyed or not. So as you construct the layout, the rules are being checked. Okay, so that's one part of it. The other part is, as I said, has the layout been faithfully translated? So you have a inverter and you've made a layout here. So it is possible that none of the rules are violated, but this one is not a faithful translation of this particular schematic. So what we need to do is, what we call is a very important step, layout versus schematic check, LVS. So what we do is from the layout we extract a new schematic. So we don't look at this schematic anymore. From the layout, we extract a new schematic. And then what we do is this new schematic is compared with the old schematic. right? The new schematic is compared with the old schematic. Do we have a PMOS? Okay, we have a PMOS here. Is it connected to VDD? All right, so this is connected to VDD. Do we have an NMOS? So a correspondence is done between the two schematics here. And is checked whether the two schematics match or not. And if they match, then we know we have confidence that we have faithfully translated this particular schematic into this particular one. So a layout versus schematic check is again something that needs to be done. And again, as we have been saying, because one is not doing a layout of an inverter or an AND gate, one is doing layout of hundreds of thousands of gates. So all these steps are, again, there is a CAD tool which will do this for you, which will extract a new schematic and compare with the old schematic and tell you whether the LVS has passed the test or not. All right, so that's something that's an important step in the design process where you compare the two schematics here. The other thing is when you extract, as I was saying in the last lecture, when you extract a new schematic from here, what you get, the new schematic is, of course, has the same structure here, but what you get is additional information. Additional information about what is the drain area of this particular transistor here. One can get that from this particular layout. What is the drain area? What is the perimeter of the drain? What is the drain area and perimeter? All those other information that we get. If there's a wire here, as you can see, there's a metal one wire here. So this wire here will also have a capacitance. So all those extra information becomes available. And so when you extract a new schematic, this new schematic has this additional information about all the areas, relevant areas, all the capacitances that are there. You see a poly wire running from here. There's a poly wire running here and all that. So the poly wire will also have a capacitance here. So one can put an additional capacitance here at this particular node here. So all these additional parasitic capacitances of the wires and all that, they all become available once you do a layout, schematic extraction from the layout here. And then if you simulate this particular schematic, you will get a correct assessment of, a better assessment of the performance here. All right. So some of the things that I want to highlight, a common mistake or common perception of many of the students is when I write 3 lambda by 2 lambda, the transistor area is 3 lambda into 2 lambda, which is 6 lambda square. Right? So when we say the width of the MOSFET is 3 lambda, length of the MOSFET is 2 lambda. So what is the area of the transistor? 3 lambda into 2 lambda. Very simple one, right? 6 lambda square. Now, or the area of this PMOS is 6 lambda into 2 lambda. So it is 12 lambda square. But where is what is this area that we are talking about, 3 lambda into 2 lambda? If you look in this is the area that I'm talking about, 3 lambda into 2 lambda, right? This is where it is. This dimension is 3 lambda, and this is 2 lambda here. So this area is what this is, 3 lambda into 2 lambda here. And 6 lambda into 2 lambda is this area here, PMOS. Right? So this is the 12 lambda square. But where is the transistor? The transistor is not just this area, right? Transistor is not this area. This whole thing is transistor. Go back and see. This is the drain part here. This is the channel part here. Wherever the poly is there, underneath the poly is the channel. This is the source part here. And this is the substrate contact here. So this whole thing is the channel. I mean, this whole thing is the transistor here. Right? Go back and see again. This is the drain area. This is the source area. The channel is under the poly. And this is the body contact here. So this entire area is the NMOS. And this entire area is the PMOS here. These are the active regions, right? So this is PMOS and this is NMOS. So what is this area? I can calculate this area here. This area is 6 lambda into 14 lambda, 84 lambda square. Very different from 6 lambda into 2 lambda. In fact, PMOS is even bigger because PMOS is fabricated in a N-well. So the overall PMOS area would actually be this. Right? And what is the area of this one? 16 lambda into 22 lambda, 352 lambda square. So the PMOS is 352 lambda square, while if you just multiply it together, 6 lambda into 2 lambda is 12 lambda square. That's not the size of the MOSFET, right? That's only the small channel area. You've forgotten about the source part, the drain part, the N-well, and all that you see here. So PMOS becomes bigger because there is an N-well that you see here. But if I look at the NMOS and I add up all the areas here, the NMOS area comes out to be 44 lambda square. Even that, you compare it with 3 into 2, 6 lambda square. So the NMOS is also considerably bigger than the simple area that you look at here. All right. So the transistors are much bigger than the sizes that you see. All right. But one transistor may take, you are seeing here NMOS. So does it really mean that if I make, let's say if I had another transistor here, right? So 2 transistors in series. This is one, and suppose here also I put another transistor here. So does it mean that the area of the NMOS would become 44 into 2, 88 lambda square? Does the area really scale as the number of transistors? If one transistor has this much area, if I have 2 transistors in series, does it mean that the total area would be 84? The answer is no. Let's look at that. So this is one transistor. I've just drawn in NMOS. Just compare the top structure here, NMOS here. This is my poly here. This is where the channel is. This is one contact. Let's say the drain contact here. And this is the source one here. This is the source contact here. Please note that this shows clearly that this N plus region extends all the way here. Wherever you are making a contact between N plus and metal, the N plus has to be there underneath it. The metal is on top of it. And the contact is which makes a contact. Right? So both of them are here. So what is the size of my NMOS here? What would you say is the size of the NMOS? This structure, right? This is the NMOS, complete NMOS. This is a complete NMOS transistor here. Now, how do I calculate the size of this particular NMOS? What are the rules? Some of the rules you should become aware of. What are the rules? Well, the size of this particular NMOS is, all right, so the width that I've drawn here is 4 lambda. I've not indicated. The width is 4 lambda. So that's the width. It's a rectangle. So the y dimension is 4 lambda. All right. Let's start counting. How do I get this? Okay. Let's start counting this. So one of the rules are that the contact that you see here, its dimensions are 2 lambda by 2 lambda. All right. So the contact is 2 lambda. It's a square, 2 lambda by 2 lambda. The contact has to be covered by metal 1 by at least 1 lambda here. 1 lambda here. At least 1. It should be surrounded by metal 1 by 1 lambda. It should be surrounded by N plus by 1 lambda here. Right? So this is 2 lambda. This is 1 lambda. And the other rule, another rule which says that the contact has to be away from poly by another 2 lambda here. Right? So this dimension, so this is 1 lambda. And this is another 1 lambda. So the total separation from here to here is 2 lambda. The poly is 2 lambda here. The poly is 2 lambda here. So can we see now that this whole thing, can you tally it? 1 lambda, that's the first one. 2 lambda, the contact here, there's the second one, 2. Then from here to another 2 lambda. Then from here to here, another 2 lambda. From here to here, another 2 lambda. From here to here, another 2 lambda, and then 1 lambda. Right? So that's the overall length, if you would like, of the transistor here. So you can see 12 lambda square, and 12 into 4, 4 is the width of it here. Okay, so that's the overall dimension of the transistor here. These are metals which are required to interconnect to somewhere. We are not including it as part of this thing. Now this is where I've made 2 transistors in series. No, 2 transistors in series here. This one looks like this one here. Now when I make 2 transistors in series, now note that I made a contact here to this transistor. I made a contact to this transistor because I have to connect it to some other external other things here. There's no need for a contact here. And for example, if I call this the source and this is the drain, so the drain and the source of the next 2 transistors are shared together. I mean, if this is the drain here and this is the drain of the second transistor, so the drain of the first transistor and the source of second transistor are shared together. And if you also note that this dimension is pretty small because I don't need to make a contact to it. When you have to make a contact to it, the dimensions are becoming larger here. Note that I have to extend, N plus, I have to extend it, cover it with metal and have a contact here. Otherwise, it can be as small as 2 lambda here. The separation between 2 poly is, the design rule says it can be as small as 2 lambda here. So you can verify by yourself. You can again go 1 lambda, 2 lambda, then another 2 lambda here, another 2 lambda here. The separation is 2 lambda here, 2 lambda, and all that. You can go forward, and hopefully you'll get this particular number, 4 into 16 lambda square. So that's the transistor area when I'm making 2 transistors in series. So note that it's not scaling as the number of transistors. If the area of one transistor was 4 into 12, the area of the 2 transistors is not simply double of this, it's just 4 into 16. Right? And then on your own, you can go ahead and look at if I have 3 transistors in series and all that, and you can figure out how the area scales. So it doesn't necessarily scale, especially if it is in series. If it's in parallel, things are a bit different here. If you have to connect 2 transistors in parallel, then there. All right. So a little bit of more familiarity. Can you recognize? Yes.
We have not shown the body.
We have not shown the body. So bodies, somewhere here we will make a body. This is one continuous N, and we will make a body somewhere here. So that part has not been included. Yes. So a body part also here one could include somewhere here, and body part also could be included here. So you're right. Yeah. So I will take this, for example, this N here. I will create a P plus region here. And the contact, same metal, maybe, let's say this is ground, the same metal would be used to short the body of the two. Can you recognize this layout? What is this doing? What is the layout of this particular? Red one, note, red one is poly. Red one is poly. Poly here. These are all contacts, and this is made in a N well, and they've used a different color here. So this is a P plus region here, and this is an N plus region here. So check if this is what, if I'm calling this the ground terminal here, this is the VDD terminal here. So this one ground, another, this is the poly here, same poly is running. So this is this poly running here, another transistor here. This is connected to, let's say, VDD here. These two are shorted together. These ends, let's say this is the drain or whatever, drain of one PMOS and the drain of NMOS are shorted together. So this is what it is. Right? What about this one? Can we figure out what? It's a little bit tedious, but I'm sure with this, once you recognize what this is, you can go ahead and figure this out. Huh? Which one? This one? All right. So if you look at, this is my transistor here, and we made a contact, and this is a metal. This is metal 1. Metal 1 is, so we made a contact and metal 1 is running here. For the time moment, forget this. Same metal 1 is running here, and we made a contact here. We made a contact here, and you would be noticing something else. Why did we make 2 contacts here? Right? We'll come there. And somewhere here would be the body. The body contact here and the body contact here. These are the body contacts here for the NMOS and body contact for the PMOS. I'll come to that. Why do we make multiple contacts? So I'll leave it for you to figure this out. What is this structure here? So you can imagine if you had to do layout versus schematic check, what would you have done? Layout versus schematic check. So you're given a layout, from the layout going where the transistor is, extract it and construct a new schematic, and then check against the old schematic. How tedious this is going to be, right? So this is simply not possible unless you have a CAD tool which extracts. So CAD tool will do what you are going to do. It will look for an N plus region. It will look for a poly. And wherever the poly and the N, this green region intersect, it will say it's an NMOS here. So there's another NMOS here. There's another NMOS here. This is in PMOS. So there's a PMOS here and there's a PMOS here. 2 PMOSes. Poly here and poly here, 2 PMOSes, one here and one here. And then you look at the metal. and you look at the metal and you see which PMOSs are shorted together, which NMOSs are shorted together. And in the layout, we usually add to the layers, we add symbols, like this particular line is VDD and this particular line is ground. So the symbols are added to the layout to indicate which is what, right? So anyway, what about this one? This is done through our simulator microwind. Note that so many contacts are being made. 1, 2, 3, 4, 5, so many contacts. And here only one contact, right? So note that this is a N-well, so this is a PMOS, and this is an NMOS. So you have a NMOS and you have a PMOS connected together. Can you also see something else? Okay, so we are calling this VDD. What does this show you? Huh? This is gate, and this is the drain, and the drain and the gate are shorted together. So what this is if I call this M1 transistor, whichever one, source and drain at this stage is not, and this is like our M2, and the gate and the drain are shorted together. Right? So this is what this particular one is. Now, why are we making so many contacts? Suppose I made one contact. Okay, suppose I'd done this. I'd made one contact only. All right. Now, note what would have happened if I'd made one contact here. Now, current is going to come like this. Note that this entire region is my source, and this entire region is drain. So how would the current flow? If the current this is metal, very low resistivity. So current comes in here, and this is the contact. So current comes over the metal one, and this is a contact. So it will go through the contact into the N plus here. And then how does the current have to flow? Current has to flow from, let's say this is source or whatever drain, into the source side. So it will flow like this, right? But it has to also flow like this here, this entire region here. So the current would be going like this, like this, like this, like this, like this here. The path of the current, whichever one, if you take the current flowing like this or current flowing like this, whichever one. So you see that if a current has to flow over this region, let's say from here to here, the current has to start from here, flow vertically down, and then flow laterally here. That's not good because the N plus region is not a low resistivity region. It has a reasonable resistance there. You don't want that. So the voltage at this particular point will be different compared to this particular point. While when you make a transistor, you're expecting that the entire drain is at one potential. The entire source is at one potential. It will no longer be there if you just make a contact here. And it's for that reason that you see here, they've made contacts distributed it all over. So current comes in, and then it can go here, and then these are all low resistivity regions. Current can easily go wherever it wants. And the whole region would be of one single potential here, and this whole region is one single potential. So the general rule is put as many contacts as possible, put as many contacts as can be accommodated in your layout. In this case, note that only one contact is possible. I mean, 5 contacts are possible, so they put 5 contacts. Now, who decides the width of the MOSFET here? This is the width of the MOSFET. That's coming from design. When you do a schematic design, you say, well, I need a MOSFET 20 lambda by 2 lambda, whatever. So the width of the MOSFET comes from there. Once you decide the width of the MOSFET from the design, after that, in that width, try to accommodate as many contacts as possible. Okay, in this case, the width of the MOSFET is small, and all that could be accommodated is one contact. You don't want to make an area larger just because of the contact. Okay, so you don't want to do that. But if you have a certain area available, put as many contacts as possible. Don't just leave, don't draw a layout like this here, and leave this entire area, empty and resistive here. Yes. No, the source and the drain, the circuit would decide. So from here, one cannot tell, right? Depending on the circuit, which is connected to VDD, which is connected to ground and all that. So, so it will get decided there, not from here. Now, as I said, in the layout, one may, whenever the person is drawing the layout, that person may mark a region as source and drain, S1, D1, S2, D2, and all that. You may mark it. And so when you extract the schematic, you can put those symbols back. You can extract the symbols also, and you can put that back. All right, so these were, the other thing is, as I said, the layout analysis we talked about, one is the area, of course, the overall area of the inverter that we talked about. The aspect ratio is another thing. So this is 3 by 1. The height is 3 and the width is 1. 3 is to 1. And the other one is the drain area, 19 lambda square, perimeter 15 lambda, PMOS, all these areas that you can calculate here. So these are fine. Some other additional information that you're, if you're doing it manually, you have to extract it. If the tool is doing it, it will also do it. Look at this poly area over field oxide. Now remember, what do I mean by this? This, wherever the transistor is, right? This is a transistor here, and all this green region is transistor. All the region outside the transistor, the active area, is all covered with oxide. And one of the words for that oxide is field oxide. So if I look at this poly here, all this red region poly here, this poly, the small poly that you see here, we have said that this poly runs over gate oxide. So that's where the channel is. But all the rest of the poly is running over field oxide. So for example, if I'm going to apply my input from here, so the input is going to come from here, and there's a little bit of metal here, but for the moment, let's ignore it. So poly is here, all this poly is here, and this poly is here, and all that. So why are we interested in this poly? This poly is running over field oxide. So there's a poly and there's an oxide, and underneath is the substrate and all that. So it adds a capacitance. So we need a length of this particular poly here. So poly over field oxide is, we can calculate how much is this area, how much is this area, and all that. All this extra area that you see here is 80 lambda square. The metal one area and perimeter at the output. This is a metal one that you see here. The area of this metal one, this part here is 60 lambda square. The perimeter, all this perimeter that you see here, all this perimeter 5 and all that is about 26 lambda. Why do I need all this? Okay, so you calculate the areas and the perimeters and all that. These are the capacitances, for example, for 0.5 micron technology. What are these capacitances? Let's understand them for a moment. COX, oxide capacitance, it says, is the capacitance, as I've been saying, underneath the poly there is a gate oxide. That's where you make the transistor. That capacitance has a value of 3.6 femtofarads per micron square. Okay, this is the channel part there. All right, so that is there here. Poly, this poly which is running over field oxide, all this poly, it gives rise to a capacitance of 0.086 femtofarad per micron square. Metal 1, this metal 1 that you see here, the first layer of the metal 1 capacitance is 0.029 femtofarad per micron square. Area, and the metal 1's perimeter capacitance, we said there's a fringe part also. So the fringe part is described as capacitance per unit length. That is 0.043 femtofarad per micron. Okay, so perimeter, there is a perimeter part here. Similarly, there's a perimeter part of the poly also, which I have not indicated. Anyway, poly is not used over large areas, it's used as a short interconnect. If you want to interconnect this PMOS and this NMOS, which is very close to each other, you may use a poly to interconnect here. May use, okay? So the areas that I just calculated, the poly capacitance, go back and see I calculated 80 lambda square and all of that. So this poly capacitance comes out to be 0.62 femtofarad. Metal 1 capacitance comes out to be 0.5 femtofarad. This metal 1 capacitance here, 0.5 femtofarad. The fringe part here, which means the ones that come from the perimeter, is twice as large as the area part. All right, it's not the area which is the dominant here for the metal 1 capacitance. Is the fringe component here. This is contributing, the perimeter here. The perimeter, if you calculate the perimeter of this multiplied by this one, this is giving rise to a component which is twice as large as the area. Alright, these all look very small, 0.62 femtofarad, 0.5 femtofarad. So we have to get used to these femtofarads and all that at this scale. The capacitances are really small. Here I've taken, now how are they important? I've taken two inverters and put them next to each other. Connected one inverter to the other. Right? One inverter connected to the next, so you can see the connection being formed. All right, the two inverters are connected together. And as we will see, once you're switching this particular inverter, you go from 0 to 1, then the output will go from 1 to 0. And 1 to 0, which means that the capacitance at this particular node has to discharge, right? So I have to know what is the net capacitance at this particular node, because that's the capacitor that will discharge, that's the capacitor that will charge here. So if I look at this capacitance here at this particular point, so node is not so simple as, this wire that I've drawn, now you can see where this wire is, where the output is, and where the outputs are here, and it's connected here. So this is how it is. So if I calculate the total capacitance, don't worry about it, how do I calculate and all that. So some capacitances come from here. What I want to write is the total capacitance that comes out at this particular point here. We'll see that later on. 12.1 femtofarad. 1.1 femtofarad is due to parasitic, poly, and M1 capacitances, basically wire capacitance. Out of 12 femtofarad. So if I had not done the layout, I would have had the schematic with me, and maybe I could have estimated a capacitance using gate and gate to source and all of that that you see here. Even then, see, gate to source and gate to drain I could have estimated from W and L. But drain to body would have been difficult because I don't have area and area of the drains without the layout. But suppose I made some estimation and calculated that. This poly and metal, I wouldn't have had any idea how long were these wires and how this metal and all that. I would have no idea. Yeah. So you can see 1.1 femtofarad compared to a total of 12. It's not negligible. It's at least 10%. But that's because I've just put the two inverters next to each other. The wires are really short. Right? So what if I end up with a situation like this? Let's say if I have one inverter here and another inverter here, and I connect it with a wire which is 100 microns long. Right? 100 microns is not too long a distance. I have a chip size of maybe several millimeter by several millimeter, and one gate may be connected to another gate somewhere far off. So this is not an unrealistic situation. So if I had this, let's say 100 micron metal one wire, width is 1 micron, then the capacitance due to the metal interconnect would have been 11.5 femtofarad. Now note, go back and how do you keep this in mind? The gate capacitances, CGS, CGD, they all add up to something like 11 or so, right? Now gate capacitances device capacitances are what? Around 11 femtofarad. When I add a wire like this, the wire capacitance is 11.5 femtofarad. 75% of which is due to the fringe component. Fringe means the perimeter. Okay, the wire capacitance is 1.76 as large as the gate capacitance of inverter 2. Of inverter 2, of the second inverter. So when you look at the capacitance here, the capacitance, some capacitance, if I write this node, some capacitance will come due to the inverter 1, some will come due to the wire, and some will come due to inverter 2. The wire capacitance is 1.76 as large as the gate capacitance. So wire capacitance is so important. If I don't, if two inverters connected together and I have no estimate of the wire which is there, how long is the wire connecting them? So my estimate for the capacitance at this particular node is totally wrong. The estimate of capacitance is totally wrong, and therefore any delay that comes about because of capacitance will be totally wrong. I have, the prediction of the delay will be way off. You may think that your IC will run at 500 megahertz. It may run at 250 megahertz because the capacitance is twice as large. The critical path would be, you have to examine the critical paths, and in the critical path, there would be a wire also there. Now, here I've written, interestingly, this is 0.5 micron geometry, and I did the calculations here. Here, wire capacitance 1.76 as large as the gate capacitance. When you go to smaller dimensions, so when you go to 180 nanometer, the wire capacitance becomes 7.5 times as large as the gate capacitance. Does it make sense? When you go to 180 nanometer, what happens when I go to a 180 nanometer from 500 nanometer? When I go to 180 nanometer, my lambda becomes what? See, for 500 nanometer, my lambda is about 0.25, let's say half of the 0.5. Right? When I go to 180 nanometer, my lambda would be half of 180, which is 90 nanometer. So all my devices have become much smaller. And as the device becomes much smaller, all these capacitances that you see here, CGS, CGD, they all become scaled by that size here. So the device capacitances become very small. While my wire, see, when I'm designing my chip, my wires are not becoming smaller. In fact, as I'm going towards 180 nanometer and 90 nanometer, because the transistors have become smaller, I'm cramming more and more components, and the IC sizes are a little bit actually increasing with each generation. So my wires are not becoming smaller, but the device has become smaller. So what has happened here? The wire capacitance, if I have 100 micron long wire running between the two inverters, the wire capacitance is now 7.5 times as large as inverter 2. There's no way that I can predict anything about the delay without talking about the wire. Right? So you can see that my delay predictions will be all wrong unless I do the layout. And from the layout, I re-extract the schematic. And when I re-extract the schematic, I will have an estimate of the wire at this particular node. So post layout simulation is the accurate simulation if you want to estimate the delay. If you just want to check whether my circuit is functionally correct or not, pre-layout simulation is fine. Whether it will, whether an AND gate or an AND gate will work as an AND gate, fine. Whether a flip-flop will work as a flip-flop, okay, you can do that. But at what speed can I run my flip-flop? At what speed can I run my multiplier? All those other things, then you have to do the layout, extract it, and add all the capacitances there. Without that, you simply cannot. You will have all wrong estimates. Okay? And these are becoming, as you can see here, the importance of wires are becoming higher and higher as you're going towards lower and lower geometries. Here it was only 75, it was only 1.76, here is 7.5. If we redo the calculation for 45 nanometer, things will become even worse. Okay, let's come back to these design rules that we are talking about. We've been saying the rules are that the poly is 2 lambda, n plus is 3 lambda and all that. Actually, these are a simplified representation. The actual rules that are there for any technology, the rules are specified in terms of microns. It will say, well, you can make your poly, whatever, 180 nanometer. The minimum dimension of metal 1 is, let's say, 200 nanometer, whatever. The rules are from a particular foundry, they are all specified in terms of actually microns. Now, remembering something is 180 micron, 180 nanometer, another thing is 200 nanometer, something else is 350 nanometer, is hard, right? So lambda, specifying everything in terms of 1 lambda has several advantages. First of all, it's easy to sort of understand what the rules are in terms of 1 parameter, lambda, and the rules are all in terms of integer values, 2 lambda, 3 lambda, 4 lambda is easier. But there is something else also important about lambda rules, which illustrates a very important way at which we look at design of large circuits. The use of lambda rules, a very important benefit of lambda rules is, use of lambda rules gives you a design representation which is independent of technology. Now, why is this important? This phrase that I have a technology independent representation of design is a very important phrase. Technology independent representation of design. Why is it so important? All right. Technology, as we've been saying, is changing rapidly. Several years back, let's say people were working at 0.5 micron technology, right? A new technology would come in at, within 1.5 years or 2 years. So after 0.5, a new technology will become available, which is 0.35 micron. Okay? After 1.5 years or 2 years. Now, if you don't start designing your ICs at 0.35 micron and your competitor does it, you are at a disadvantage. That company will offer higher speeds and things like that, will take advantage of a better technology. So you have to also move. You have to take advantage of a new technology, 0.35 micron. After another 2 years or 1.5 years, 0.25 micron technology becomes available. After another 1.5 years, 0.18 becomes available. And then 0.13, and then 90, and then, so technology has been rapidly changing. Right? So it's rapidly changing, and along with that, circuit complexity is continuously increasing. Now, if you are a company which is designing chips, what you have to do is, you have to design increasingly complex circuits, and how much time do you really have? new technology is coming into, every 1.5 years. You don't have a lot of time to bring out your design into the market here. So what you have is almost like a fixed amount of time in which you have to carry out increasingly complex designs. Increasingly complex designs you have to carry out in a reasonably fixed amount of time. So how do you do that? Let's say you have a team of 10 people doing a design, right? 10 people doing a design, and it's 1 million transistor design. Okay, 1.5 years later, you have to do a 2 million transistor design. Do you hire 10 more people? Does the design team become 20 million? What happens? And then then you have to do a 4 million. Do you hire another 10 people? Because design requires time, right? So what do you do? How do you do it? Well, so you realize that the IC designers have been under constant pressure to design more and more complex ICs in about the same time. So how do you do that? How do you cope with increased complexity in a fixed time? Well, one of the strategies that you can use is that you don't do every design from scratch. I mean, if you're a microprocessor company, it doesn't mean that all the registers, all the ALUs and multipliers and everything you do from scratch. It doesn't make sense, right? So one of the ways in which you cope with any complexity is you reuse. Something that you've designed earlier, for a new design, you reuse that particular part there. So reuse will drastically cut down your time. If a multiplier that you had designed earlier, and now in let's say 180 nanometer, you've done a multiplier design, and now you have 90 nanometer technology. Now, if you can take that whole multiplier that you had designed and use it at 90 nanometer, you will save all that multiplier design time. But then, remember, design of a multiplier means what? Design of a multiplier means schematic design and all that. Plus, it means the layout. Now, the layout has been done at 180 nanometer. Now, how do you take a layout done at 180 nanometer? Because all the dimensions are what? According to 180 nanometer. And now you have to transfer the design to 90 nanometer. 90 nanometer will have its own set of rules. And 180 nanometer has its own set of rules. Now, how do you transfer the design from 180 nanometer to 90 nanometer? Well, so reusing a design becomes very easy if I had done the design, everything in terms of lambda. If all my design had done in terms of lambda, so for 180 nanometer, lambda was 90. And when to go to 90 nanometer, all I have to do is make lambda equal to 45. And my design is ready. I don't have to do the layout again. It's so simple. The whole design of a multiplier which was done at 90 nanometer now becomes available at 45 nanometer. All right, but it's not as simple as that, right? There is a price that you have to pay for it. And what is the price? You're realizing why, what is lambda? A layout done in terms of lambda is what? Is technology independent. Because there's no technology information in lambda, right? Lambda could be anything. 0.5, 0.35, 0.28. So it's a technology independent representation. And whenever a new technology comes in, you just change the value of lambda and you're ready, right? So the idea of this technology independent design can be illustrated through these two cases here. In one case, what you have is you have a specs and you do a design, and design, of course, takes technology information and you get something, let's say the final layout, which you can send to the foundry. That's one way of doing the design. The other way of doing the design is this. You take specs and you do design at a higher abstraction level and you get a technology independent design. And then you add technology information and you get the final design. So you've broken the design into two steps here. One is a technology independent design step, and another one of them is where you add the technology information. So note that this part can be reused. This is technology independent. As you go from one technology to the next, to the third and all that, this part can be reused again and again. While this part is something that you will have to carry out for each technology. Technology mapping, you have to add technology information to get the final design. Now for lambda, the adding technology information is very easy, just changing the value of lambda, right? So you have to make sure that this part is also simple. If this part is difficult, then again it will consume more time here. So coming back Although lambda rules make technology mapping easy, they result in inferior design. Let me illustrate using some simple cases here. You will see in a minute that lambda rules will represent worst case rules. Okay, for illustration, let's look at this. Let's say I have a technology 1 micron. And remember what the rules are. The rules are what they specify dimensions of different lines, polyline and N plus and all that. Okay, so let's say there are 3 dimensions, L1, L2, L3. And the actual rules are that L1 has to be 1 micron minimum size, L2 has to be 10 micron, L3 has to be 3 micron. These are the rules for 1 micron technology. Well, for 0.5 micron technology, let's say the foundry says the rules are, this is 0.5 micron, this is 3 micron, this is 2 micron. Let's say the rules are here. Now I want a technology independent representation. So what lambda value should I use? Let's say this is the minimum. What lambda value should I use? Can you see that what I can do is the following? Say I specify in terms of lambda. So I say lambda is 0.5, first one. First one, lambda is 0.5, then this becomes 2 lambda. This rule becomes 20 lambda. This rule becomes 6 lambda. Well, for the second one, I specify lambda is 0.25. The rule becomes 2 lambda, 12 lambda, and 8 lambda. The rules are different. At each technology node, the rules are a bit different, right? This rule is still the same, 2 lambda, but this rule has become 12 lambda. And this rule is whatever, 8 lambda. Now, if I want a lambda rule which is valid for both of them, what will I do? What rule will I use? I'll look at these and say, well, the rule is 2 lambda. If I look at both of them, what will I say? The rule is 20 lambda. Oh, sorry, 12 lambda. 12 lambda will be valid for both of them. And then if I look at both of them, I'll say the rule is 6 lambda. So if I want a technology independent representation, what rules will I end up using? I'll end up using a common design rule, which is 2 lambda, 20 lambda, and 8 lambda here. Rules will be very conservative, in some sense, worst case rules. So I have to look at technology, as I go from 180, 130, 90, and all that. If I come up with a very conservative set of rules, then very conservative, which means those rules are going to be obeyed anyway. They are the worst case scenarios. They'll be obeyed anyway for all these technologies here. But what am I doing in the process? Look, when I'm using a lambda rule, I'll use L2 is 20 lambda. But this technology actually allows 12 lambda. I'm not taking benefit of the whole technology. So there's a price that I'm paying. I'm using simplified lambda rules. I get a technology independent representation. I can very easily port my design from one technology to the other, but I'm not taking full benefit of each technology. All right, so the lambda rules are benefits of scaling to some extent are lost. For example, this says you can use 12 lambda, but I'll continue to use 20 lambda. All right, so lambda rules have benefits, and you can see disadvantages also. All right, let's stop here and then